Yeah, so I'll apologize ahead of time. I do similar work, to the value added and teacher effectiveness kind of stuff in healthcare. And my disclaimer, I actually have a company with a couple of surgeons that does this stuff for surgeons, for surgical collaboratives, improvement collaboratives. So if I say patients and doctors and hospitals in place of students and teachers and schools, you know why. Like, I regularly make that mistake. So
You think some of our students are patients.
yeah, exactly. So I don't really think of the fourth grade students as patients. It's just what I'm used to talking about. So this is the one of the projects that came out of this Gates-funded Measures of Effective Teaching project with a huge cast of characters involved with it, including people from here. But this paper, the main authors are Tom Kane, who's out at Harvard, Dan McCaffrey and Trey Miller, who were at the time were at Rand. Dan's now at ETS, and me. But there's an enormous number of other folks, unnamed, named in the paper, but who were involved. It was one of these things where it was just astounding that Tom particularly was able to get so many people to work on this and really put in a lot of effort and not worry about credit, right? Like, it just got a lot done. One of the things, just as a prelim kind of sales pitch, all the data is archived at ICPSR, including all the 70,000, 90,000 hours of video and all this stuff. So, and you can get access to that. You have to go through some hoops to get the privacy issues dealt with, but to get permissions. But it's all there. Okay, so this is the study that's really about trying to take these, look at measures of effectiveness and validate them through random assignment. So let me kind of give a little context. So I think people here probably know, but I want to be sure we're all on the same page, right? That there was this big non-experimental literature on teacher effects that I'd summarize kind of as following. Teacher effects on state tests or on test scores. Roughly finding that standard deviation across teachers between 1/10 and 1/4 of a student's standard deviation, which you can think of as 2 to 5 percentile points each year. So these, we'll talk about these, are basically run a regression control for a bunch of stuff, and how big is the teacher effect in there, on test scores. The 2 to 5 percentile points, is that big? Is that small? Right? Or 1/10 to 1/4, right? It's kind of a couple ways to think about that. One is the gap between blacks and whites, or rich and poor, is somewhere between 2/3 and a full standard deviation. So that gives you one way of thinking about it. Another way to think about it is the gap between a rookie teacher and a more experienced teacher is a little less than 1/10. So these effects are thought of as fairly big in the overall teacher thing. And the key findings out of this non-experimental literature that I think have been driving thinking on this are, the first is that the traditional credentials, master's degree, certification, things like that, don't seem to be very related to these non-experimental teacher effects, to value added. There's some payoff to experience. Teachers get better in their first 3 years, about 1/10 of a standard deviation, maybe a little less over the first 3 years, but then flattens out on average afterwards. And then the only way to try and identify teachers who differ in terms of value added, or the most effective way, is if you take 1 to 2 years of prior performance on value added, it's correlated and can predict future performance of the teachers. So let me just kind of give you an idea of this, of the magnitudes. This is a picture from LA that plots teacher value added estimates, the distribution. There are 3 curves there, which I won't ask you to differentiate between, and that's the point of the figure. That one is traditionally certified, one were alt certified, like TFA and some other things done in LA. And then the last curve was completely uncertified, which at the time there were a lot of uncertified teachers in LA. This is from a while back. It's grades 2 through 5, elementary teachers. It's math. But the point of this, and this kind of summarizes the literature, is you don't notice the difference between those three curves, right, between the distributions. What you know, but within each one, there's a lot of spread. Certified, uncertified, whatever. There are lots of very good teachers and these are these value-added measures, so on the observational, whose kids are 5 percentile points further ahead than you would have expected based on their characteristics at the beginning of the year, and others who are 5 percentile points behind. That would be a pretty huge swing, right, from if we think it's causal and real, right? This is the same thing, just instead ranking teachers based on their first 2 years of value added, putting them into quartiles. And the curve on the right is the people who are in the top quartile in their first 2 years. Curve on the left, teachers in the bottom quartile, et cetera. And this is their performance in the third year, right, after their first 2 years. And again, what you see is, the first 2 years really do distinguish. On average, there is about a 5%, 10 percentile point difference between the top and bottom quartile. But again, still some spread. It's not like it's perfect. It still leaves there are good and bad within each of these groups based on their first two. So useful information, but not perfect. So this kind of information, I think, like those kind of graphs, I think really drove the debate for a while to people to say, well, we've got to somehow start using this information on actual performance in the classroom. That really got, in some sense, way out ahead of the evidence, right? So, I mean, the number of states now using value added for teacher evaluation pay promotion is really growing. It's really getting used. And I don't have to, everybody in here, I'm sure, has been skeptical about value added. I certainly was going in. The idea that you can just run this regression and the teacher effect is the causal effect of teachers, and I have good enough controls to deal with all the kind of student sorting and selection should make, everybody should be skeptical of that. So we need some really strong assumptions that had been untested, but recently there's been some evidence that make it sound like maybe they're okay, supporting causal effects. So in addition to the study I'm going to talk about today, there are kind of, I think of 3 others. There was, people have looked at Project STAR, and there are 2 ways you can think of that. Project STAR was the classroom randomization where kids were randomized to teachers as part of the class size experiment. And there you get similar variation across classrooms when kids are randomized as you get observationally. That's not a teacher effect, it's a classroom effect. It might be something about the peers and the way and things that happened in that classroom that year that doesn't stick with the teacher. But at least you saw similar kind of variation. And that variation has been, Chetty et al. Have some papers that document that it's related to those kids' long-term outcomes, earnings at age 30. Right? Tom Kane and I had a study in LAUSD where we randomized 78 pairs. So it was a small study, 78 pairs of elementary school teachers to classrooms. We had observational. It's going to be very similar in structure to what we're going to do today, but much smaller scale. We had observational data from on value added for these teachers from before the randomization. We used it to predict the difference we'd expect when we randomized teachers to classrooms, and then saw in the randomization what was the actual difference in test scores, and they lined up fairly well on average. So if we thought, for the teachers who we thought one teacher would be 1/10 of a standard deviation above compared to the other, on average test scores were 1/10 of a standard deviation above. And then Chetty et al. Have a nice, huge data set, quasi-experimental pair of papers, where they basically look at when a new teacher comes into 4th grade. You have that teacher's value added from other years. Do you see when that teacher comes in, the test scores go up by the amount you'd expect based on how that teacher's value added differs from the teacher who left, from the teacher they replaced? And again, find that it's a pretty good guide, and then they do a great thing. They're able to then look at those same kids years later, and it's related to earnings and teen motherhood and all kinds of stuff. Okay? So what we're going to do is is a larger scale random experiment that complements kind of this earlier work. So what we did was we had 1,600 teachers, a lot of grades, 6 large districts, so generalizing in that sense, who were going to randomly assign to classroom. This is all done within, think of, you get 2 or 3 teachers, or sometimes up to 5, within a grade and school, who the principal says we can randomize them, and they let us randomly assign. And I want to be a little narrow about what we're estimating and what we're going to be testing, right? So what is this randomization bias? It gets an experimental estimate of what I'm going to call the parameter that we're interested in trying to figure out whether value added is capturing that. And the parameter is really narrow. So let me state it narrowly. So right, I want to think I've got these 2 classrooms, or I've got a classroom of students, and I want to ask the question, if I gave them teacher A versus teacher B, will their test scores be higher at the end of the year, their state test scores, by the amount that I thought they would be based on value added? Value added is supposed to be estimating that causal effect, the causal effect of teacher A relative to teacher B on the kids' test scores at the end, state test scores at the end of the year. So that's why I don't want to call it teacher quality, because it's narrow. And the one thing is, like, I'm not saying anything about why, right? It's a black box. Might be that one teacher gets the parents to do a bunch of work, or I don't know what, right? It could be all kinds of things. But all we know is that if the kids had that teacher instead of the other teacher, they'd have higher state test scores at the end of the year. Maybe nothing else, too. Like maybe other things are going wrong.
So if the principal or something says, well, these 2 are interchangeable, so you can randomly assign, what proportion of teachers is that, and does that reflect what we would get on the classes where I'm sure you've gotten this a billion times.
Like, in other words, external validity. For example, what we're most worried about is they're going to say, oh, these teachers are really similar, and I randomize them anyway. Yeah. I normally randomize these teachers anyway.
But there are these other teachers that are very different,
yeah.
And that's what's biased.
And I'm going to say a bit more and show you some tables on this later, but let me summarize. The one place, the teachers who we clearly weren't getting are the teachers who are specialists in English language learners and special ed. And so we lose those specialty classes, and they told us, oh, we can't, we only have 1 teacher in that grade who's certified for this, and we can't randomize. So we lost those. What I'm going to show you, though, is the teachers who we have left. So after you kind of lose a little bit of I think of it as the bottom tail in terms of academic performance. But once you get rid of that, the teachers we have virtually identical value added and distribution of value added compared to other teachers in the school and teachers in non-participating schools. In terms of, so it didn't look like we got all great teachers, or at least on value added measures. And the other thing was the sorting issue. So we have a table that I'll show you where we look at, for these teachers who were in our sample, how much were they getting, how much variation was there in like baseline sorting, like if you look at the average baseline scores of the kids the teacher got, how much variation was there in the teachers who we have in our sample compared to others? And it's big, and it's almost as big, not quite as big, as you see from other teachers in the school or other teachers in other schools. And we think the reason it's a little less is because we lost all the special ed classes at the bottom. But I mean, the amount of sorting going on, and this, I'm like amazed people let us randomize teachers to these classrooms, because the amount they're tracking and sorting kids is somewhat astounding to me, right? The standard deviation in baseline scores across classrooms, even in the teachers in our sample, is like 0.4, right? So that's like almost, you'll see classrooms that have a full standard deviation difference in average baseline scores in our sample that they let us randomize, which I'm somewhat shocked by.
And then one more question, which is the cross-school issue. So how much of the variation is in the value addeds that you use is across schools rather than within schools, so that we worry that that's biased?
Yeah. So let me answer that 2 ways. One is, this will, of course, depend on whether I put in some kind, when I estimate value added, do I somehow remove school things? So do I control for school average free lunch in the school? That gets rid of some.
As long as it's not school fixed effects.
Or if I put in school fixed effects, that'll do it too. Turns out, even if you put in school fixed effects, it's something like, there's lots of variation left. I don't have a concrete number, but I should have a concrete number. I always think of the school effect as like less than 20% of the total variation in what you see in value added, and I think it's even less, but I don't have that number at my fingertips. So in other words, like, it's not, I don't think there's still an enormous amount of variation within schools, but it is true, we're going to learn in this experiment only about within school variation, because all the randomization is within school. We never get to take a teacher who looks good in school A and put them in school B. And most of the value-added information that we have on these teachers was in the same school. Not all. Oh, no, I take it back. All of it in our data. In this data, we're going to just use value-added from the prior year when they were in the school. So it's very much, in that sense, we don't answer the question, can you take teachers can you compare teachers across schools? Right? And that's limited. Okay? But so our idea, what we are doing for this within-school experiment is asking the question, okay, I think of value added as, if I think of value added as answering this causal question, how much does one teacher have an impact on end-of-year state test scores compared to another? Then with the experimental estimate, I can see whether my value added estimates from observational predict what we get in the experiment, and that's a way to validate the value added. This is, Raj Chetty calls this forecast unbiased. So it's not, I want to just be a little careful again, a little narrow. It's not telling me that for every individual teacher the estimate is correct, right? The estimate will be off. It's saying that of the teachers who I say are 0.10, so a tenth of a standard deviation higher than expected on value added, on average those teachers are 0.10. Some might be better, some might be worse, but we're getting it right on average. So there's spread within, and some of that difference within might be systematic. Like, we're never going to get it right for that teacher no matter how much data we get. All we know is on average we're getting it right.
But a really simple forecast unbiased estimator is just estimate them all as 0.
Yeah.
So
0.
The question isn't that it's forecast unbiased, because you could come up with that kind of estimator by giving them all zeros. But the question is, how much better is it than assuming they're all the same?
I mean, I guess
That's what's not clear to me from this way of estimating.
you're right. I guess one way to say it is, if this is forecast unbiased, suppose I think this measure is forecast unbiased, then I can take the estimates and I know how much variation they're predicting in performance. And now I can think about comparing it to other ways we have. But at least now I know the value added estimate, the range that they're predicting, is truly the range that we'll see, right? So in some sense, and you'll see, like, another way to think of it is, at the very end I have this one table where we could think about various ways to break up value added into pieces. The piece that I would have thrown away if I would have controlled for peer effects, and the piece and the rest. And this also will let you start saying, okay, I'd like to use both pieces because that gets me more variation, more prediction, but I want to validate both pieces. Are they both forecast and biased before I add them together? And so it lets me take pieces at a time and check, is another way to say it. But I agree, like, I know I used it. I mean, I can create a forecast unbiased estimate based on really lousy stuff. Based on your credentials and master's degree. Well, I don't know. Those are such bad. I mean, those would basically be predicting 0 for everybody. But you're right. 0 is forecast unbiased. But it's not a good predictor in the sense of it doesn't predict any variation. Okay. So this is the game. This is the goal and where we're heading. Let me summarize and then show you the picture that summarizes the results, and then we'll kind of work through the details. So I think the first thing is, after random assignment, which we do in the second year, the teachers and I'll talk about how we do this, who we had greater measured effectiveness in year 1, in fact, produced higher student achievement on average. So that just says at least we're getting the direction right? Like, these guys are better teachers. Or, I take it back, they're having impacts on state test scores at the end of the year. Right? Like, that's not necessarily better. We care about lots of things other than test scores. they're unbiased, forecasts unbiased in the sense that the spread that we expected, the magnitude that we thought they were better, was consistent, right? So what we saw in the experiment was consistent with what we predicted, which we're going to end up running like what we get in the experiment on the left, think of it, and what we predicted on the right, and we're looking for a coefficient of 1, right? Do we get that coefficient of 1? And we get a coefficient that's very close to 1. And then, we don't just care about that, so we wonder, are there other things, like if we only saw it on the state test and not on anything else, we might be concerned, right? So we gave a supplemental test, supplemental assessments that were supposed to be more cognitively demanding and stuff, and we saw that those students also had, instead of test alternative assessment test scores going up by a full standard deviation, they went up by actually 0.66, about 2/3, 70%. So those students assigned to high value added teachers on state test scores also did better on the alternative assessments. And they also said they were a lot happier in class, which was my favorite measure going in, not other people's, so I was like, yes. Because I thought they'd probably be like, oh, taskmaster, you might think it would go the other way. We look at some other things that I'll talk about where you don't see much. It doesn't mean that there aren't teacher effects on that. It means they're not related to teacher effects as measured this way on state test value added. Okay.
Sorry, did it vary by district, the 70%, like the ones that had tests that were better, or something like that? Did you see it?
Unfortunately, we're not very powered to find a lot of variation by district. So, the answer is nothing significant, but I don't think that necessarily means it didn't. I think, my guess is, and this is one of the things I think going ahead, I think to try and find differences across districts, you need a more concrete idea and model going in about which districts you expect, so that you can group the districts in a way. And we didn't have that, so we just run it separately in all the 6 districts and test whether it's significantly, whether you can reject pooling and you can't reject pooling. But that's a low power test. You could get higher power by having a more focused model going in. Okay, so here's the picture that summarizes. So on the x-axis, okay, so what are these? We took all the teachers. Everything is going to be normed relative to your randomization group. So we have like 2 to 5 teachers within a randomization group. On the x-axis is what we predicted the students assigned to that teacher, what would be their teacher's predicted achievement. So that's the value. This is predicted value added based on prior data. It's a little different than that because we had big compliance problems. So if we assigned you to a teacher who had really high value added, because of compliance, we expect you actually got teacher a little less, not so good on value added. This is that prediction. So I think it's like a prediction from a first stage. And then on the y-axis is going to be the average of their actual achievement after random assignment. And what we did was, based on this prediction on the first stage, we binned you into 20 groups. The top 5th, the top 20th, the next 20th, into 20 equal groups. And these are the means in each of those groups. So this basically summarizes the regression, right? And what you're seeing is, right, this was a teacher, these groups of teachers, students assigned to these teachers, we expected their teacher effectiveness was about 1/10 of a standard deviation higher on math relative to the other students in their randomization group. And in fact, they came out about 1/10 of a standard deviation higher on their actual test scores after random assignment. And same down there. And right, you can see there's a fair amount of spread. The 2 tails are going to be helpful in kind of pinning this down. But even without the 2 tails, it's reasonably linear, and there's some noise around there. Remember, these are already average. There's about 40 teachers, I think, in each one of these that have been averaged into each one of these. The individual teacher level, there's much more spread. But this is, on average, we're getting it right. And that 45-degree line would be what you'd expect if it was forecast unbiased. On average, you get it right, and you're pretty close to that here. This is for ELA, English Language Arts, and it's on the same scale. And it kind of highlights that we just don't predict as much variation across teachers on impacts on ELA, which is a standard. And so you have a lot less power here. But you'll also notice, like, it is true, like, if you fit the line here, it would be flatter. And when we estimate just on ELA, it's flatter, but it's not significantly different from 1. But, we don't have the range to really get a precise estimate with ELA. The big headache and the problem with this study is the teacher you were actually assigned to were much more different. And so we had a lot more spread, a lot more power if everybody would have complied. But compliance meant teacher you actually had wasn't as effective as, on average, as the one we assigned you to. So we ended out with a lot less power because of lack of compliance.
So what's the R squared if you did this on the individual teacher data instead of the bins? Because the bins always make me nervous that you're making it seem vastly more predictive.
Oh, no, I think, and actually we could do this straight from the think of, this is saying
you get the same slope, but the
here,
individual level predictive power is very weak, and there's a lot of scatter around that line.
here's a way here's I think the best way to think of that. So the predictive power we get here is the same as the predictive power you get in observational data because we end up getting a coefficient of 1. In observational data, with 1 year of value added, and we have some other stuff that probably improves this a little bit, but with 1 year of value added, you can predict 30 to 40% of the teacher level variation in next year's performance. Now, teacher level variation, on top of that, there's a classroom, year-to-year classroom effect, and on top of that, there's the noise from 20 students. So in terms of the total variation, I think that's about 10 to 15%, right? So I think that's a way to think of it. So we really could think of these measures as probably explaining 30% or something of the 1 year of value add explains 30 to 40% of the teacher level variation next year. So there's still a lot left on the table. It's getting it right on average. It's useful, and it is like in these you can see it is predicting big differences, but there's a lot left on the table that's not being predicted by these. Right? We'd like to predict a lot more. Right? And most teachers, right? So there's the outlying 5% on each end, outlying 10. You're starting to get pretty narrow range of predictions once you're, for 70% of the teachers. And maybe 15%, the last 3 bubbles on each end is where the most important action is in terms of what we can predict with 1 year. With more years, you do better. So, okay. So that's basically what we're doing. And now it's just, okay, how do we get to these numbers and showing you some stuff along the way, right, of where this all comes from. Okay. So what I want to do, I'll tell you a little bit about the metadata and the experimental design. Although you guys are probably a lot of you are pretty familiar with this. I'll talk about how we got the observational, the pre-experimental estimates of value added, and the predictive effectiveness for each teacher. We do something a little funny there that is like a poor man's empirical Bayes or a poor man's hierarchical modeling. And then I'll talk about these things, the external, like how our sample compares and show you some evidence. The internal, like after randomization, how do we do with attrition and balance and things like that. The non-compliance is the big headache. This is where you learn trying to go really fast, you pay a price, right? I think we probably could have done better had we not been under an incredible timeline. Just so you know, this project, I remember we started, I guess it got funded in April. We were in the schools that fall. I mean, you were drinking water through a fire hose. Okay, and then we'll get to the results on these tests. Okay. So here's who's in it. Yeah? Oh, no, sorry. Here's who was in the experiment and the data. So this is this MET project. So we have 7 districts, although Pittsburgh didn't participate in the experiment, so really 6. But, they're big urban districts, pretty standard big urban districts. We're going to primarily have 2 school years. The first year, 2009-10, we're going to collect a ton of data observationally. 2010-11 is the randomization year where we randomize teachers. we do grades 4 through 8, ELA and math, and then high school we have ELA, algebra, and biology. In the paper, we do the high school. Today I'm just going to talk about the grade 4 through 8, ELA and math. Part of the issue with high school is grades 4 through 8, we have state tests, so everybody gets tested, or almost everybody. In high school, we don't have those, so it's all based on our own assessment, and we could not test the entire school. So any kids who moved out of one of our participating classrooms, we didn't get a test on. So there's much more attrition issues going on, missing data. It doesn't look like it affects the balance and stuff in high school, but it makes those results a little bit more tenuous. This were all these teachers were participating and volunteered in, and like the unions in all the districts were supporting the project. I think Tom basically convinced them, at least we're doing something other than test scores in this project, right? Other than us, you're basically living on test scores. Okay, so that's the project. We actually also had 1 year we had a 2008-9, and I'll show you how we use that data on value added. So just the randomization, before I talk about all the data, is really simple. We asked the principals to create rosters for classrooms. So we didn't randomize kids because principals wanted to arrange rosters the way they, I need Joey with Billy or whatever. So they created rosters. We had a date where they were supposed to send us the rosters, and then we flipped a coin and we assigned, they had a group of teachers who they said could be exchangeable. So in elementary school, this is 3 4th grade teachers. In middle school, it's tricky. 3 7th grade math teachers who can be changed based on the scheduling, which is always tricky. But they would find things like this. So then we flipped the coin. We sent it back to them and said, okay, here's how we want you to assign the teachers. That's where a lot of the compliance problems happened. And they said, oh, we already mailed the class lists out to parents. I'm like, guys, that was the whole point of this experiment. They're like, oh. So there's a lot of problems with compliance. But once we assigned rosters, that's our intention to treat sample. Those are the students that we're going to be looking at. And from there on, we can't start dropping guys because they didn't comply. And then we've got these predictions for all the teachers, both the ones who are participating, but actually for all the teachers in the school, of their expected effectiveness, impact on state test scores, and compare predictions to the actual. Okay, so that's the randomization. Pretty straightforward. Let me talk about the data we got. So it's really, and this is the data you can get your hands on and use, with permissions from ICPSR. So a lot of different ways of measuring teacher performance. So we have classroom observations, which I'll talk about in a second, which we measured. So these were videos of teachers in the classroom. We measured on a bunch of different instruments. There was Frameworks for Teaching. There was Pianta's Class. There was a specific one for math, a specific one for English language arts, all scored. We're going to use, everything I'm going to talk about here, we'll use Frameworks for Teaching because they all got similar answers. We have student surveys, this tripod survey that Ron Ferguson developed. That's basically a pretty good student survey of students' experience in the classroom. I just want to be sure, 1.5 hours or hour? 5. Perfect. I was suddenly in a panic.
I can't add, but I can tell you in advance.
Okay, no, but yeah, I'm good there. So we've got, the student surveys, this tripod survey, which I'll show you a little bit about what it does. And then all these value added on state tests. We started with 3,000 teachers. We ended out, a lot of them weren't around anymore when we wanted to randomize, or didn't have another pair anymore in their randomization group. The scores of the actual videos, right, they got scored over 20,000 times by different raters and all this stuff. We ended out scoring, I'll talk about that in a second. Just the magnitude of getting trained observers to score this was an incredible, that's where a bunch of the money in this project went to. It was building the process for scoring video in a way that was reliable and trained the observers and gave them every day you check to be sure they're doing the right thing. You give them test videos and stuff. It was a huge undertaking. And then a lot of students doing both these surveys and some supplemental assessments that we give them. And then we do have, and we haven't used it, I think some people are starting to now, but there's also some principal and peer observers, not just these trained observers. And then we're going to have, in terms of student outcomes, so we've got the state math and ELA tests, which are standard. These supplemental tests, balance assessment of math and the SAT-9 open-ended, which are are basically much more challenging tests than usual and cognitively challenging. And the open-ended was actually written answers, which may be different. Right? We found some really interesting and earlier work that the teacher effects on ELA are always kind of small. On the SAT-9 open-ended, there's much bigger teacher effects. Bit puzzle about why, right? And is that because the SAT-9 open-ended is a writing test, not a multiple choice reading comprehension test? And we don't know, but it's interesting. And then we've got these student-reported outcomes. So there's some, basically questions about how hard you worked in class that were turned into a scale. The enjoyment, how much you enjoyed yourself in class. Grit, because that was the hot thing of the day. So we have a grit scale. We have some other scales. I'm now at my total knowledge frontier on grit. Right? That's all. That, and I know I took it once online and thought, I don't see why it's a big deal if you start projects and don't finish them. As someone who's done that quite a bit. So anyway, so we've got a bunch of these outcomes on students and can look at impacts. One thing, so just to pause there for a sec. So everything we've done is about measuring teacher performance on state test scores and then seeing if that predicts, the state test score impact when we randomize. You could have used this data to estimate teacher effects on other things in the observational data and then use it to see if those are valid and predict, those other things when you randomize teachers. And we just haven't done it yet, but it's an interesting question in itself, right? We don't only care about test scores. Maybe we care. I think we don't have grit in the first year, only in the second. But, you could do this on supplemental tests, on the student surveys, et cetera. Okay. So let me talk a little bit about the specific measures. So, and you guys may know a lot about these. I never know, based on the audience, how much of your life you've spent learning about classroom rating rubrics. So we're going to use these FFT, Frameworks for Teaching. This is the Charlotte Danielson approach, but it's a subset of it. So there are 4 classroom environment kind of categories and 4 instruction categories. And within each of these, there are some sub-questions that are very specific about what's going on in the classroom as you watch this video and that are being scored. There were 4 lessons on each teacher, and they were each double scored. And then we averaged all the scores and created basically one standard score that is kind of like, average them all, and then standardize it to mean 0, standard deviation 1. So pretty simple. Not clear that's the best. You could imagine finding other ways to try and score this. But this is pretty much, if you were going to do a first principal component, the average score is pretty much the first principal component of all these dimensions. So that's Frameworks for Teaching. And it was all done with this Google, I think of it as like the Google Street View 360-degree cameras, parabolic cameras in the classroom and with good sound and stuff. So you get used to it after a while watching a classroom doing that. So you can see the kids and the teacher. Okay. The tripod, the student survey, is a survey that asked a whole bunch of different questions in these. Ron Ferguson puts into the 7 C's these different ways of thinking about what's going on in the classroom. And let me just show you some of the data to give you an idea. And these are interquartile ranges across teachers, across classrooms, in % agreeing with various questions in each of these categories. So this is this caring dimension. So they asked teacher, my teacher in this class makes me feel that she really cares about me, right? The 25th percentile classroom, only 40% of the kids agree. The 75th percentile classroom, 73% agree. So the key is, these questions are fairly focused, and they range. You really get a lot of range. Kids are able to distinguish. You get a little less range in elementary, but not that much. The elementary kids are able to distinguish, too. Not surprisingly, middle school kids are more willing to say, I hate to say strong things about their teacher. My favorite is the control, the classroom management dimension. This dimension, by the way, is pretty correlated, well, as correlated as anything with the classroom management kind of part of Charlotte Danielson. And these are things like, our class stays busy and doesn't waste time. There's some classrooms where 36% agree with that, somewhere almost 70%, and that's the interquartile. So there's a huge amount, people really see this. There's a lot of variation. And these things in observational data are correlated with value added and are pretty persistent, correlated from one classroom to the next. Teachers who look bad in one classroom look bad again in a different classroom. Okay, so those are the kind of non-traditional measures that we have on teachers. Value added, I think, is fairly standard, and you guys have probably seen a lot of value added. So there are lots of different ways. But a lot of times you do it in hierarchical models. We're going to split this into two steps. First, we're just going to run a regression. This is my favorite way to do value added. Where on the left is this so this is in observational data. On the left is end of year test score for each kid. You got a bunch of controls, X on the right, student demographics, free lunch, program participation stuff. You always put the key to value add is you put the baseline. Let's see if I can get this. Oh, yeah, there we go. You put the prior year, end of year score on the right and control for it. I think in these we only controlled for it linearly. Sometimes you put in a cubic or something. We did linear. And then in our preferred specification, we also included peer measures at the classroom level that measure like percent free lunch in the classroom, average baseline score in the classroom. So put in those. Not clear you want those in, but for our baseline we do. And then we just ran this regression and took the average residual, and I'm going to call that teacher value added. So that's not shrunk yet. With shrinkage, that's still the noisy measure of the teacher effect. Okay. And we did that for state test scores. We did a similar thing, just for consistency. The student survey, take the tripod measure for each kid and put it on the left, same controls on the right. We don't have a prior year tripod. So we control for prior year test score, just run exactly the same. And same FFT, that's a classroom level measure, not student level. So we regressed it on at classroom averages. That doesn't matter, it turns out. Though, adjusting these two doesn't make a big difference. And I'll show you how how different adjusters matter for the value added measure toward the end. So, and then we did this by district grades. So ran a bunch of different regressions, so very flexible, probably a little over more than we needed, but that seems like the standard way people go at this. Okay? So that's value added, but this estimate is noisy, and so we've got to do some shrinkage. And we want to get a prediction of the teacher effect on test scores that uses this information, but also uses those other two measures. So we want to predict how the teacher will do based on all our performance measures. So here's what we did, and it turns out this is we have another paper where we have a very similar, where we show that this approach gets you answers that are like correlated 0.98 with a full empirical Bayes approach to doing this. And I like this because it's fairly intuitive. And it turned out, for a number of reasons, it's very easy to implement in our data where the full empirical Bayes is not. So think about the goal is to take all the measures. We have all these measures from our observational year, 2009-10. We have the value added residual for the teacher. We have their frameworks for teaching, which we've adjusted. We have the tripod, and we might have some characteristics of the teacher, their experience. Experience isn't that useful, but certification, master's degree. And the goal is to combine all these to predict how the teacher will do next year. And that's what empirical Bayes does, right? It says, take all these measures and get a best prediction of the persistent part that will still be there next year. Well, a fairly natural way to think about running that regression is instead of predicting next year, predict last year. Right? You're trying to predict how this teacher will do in a different year with different kids in a different classroom 1 year away using all the data I have this year. So we basically just ran this regression. This is, in principle, what good empirical Bayes is doing. It's trying to get you a prediction of how they'll do in a new setting of the teacher effect with new data, conditional on all the current data. So, and the nice thing about this is, some teachers we didn't get tripod on. So we run this regression for all the, on the remaining variables using all the teachers who had data on the remaining variables. We want this prediction not just for our teachers who participated, but you'll see in a second, we need to know when a kid ends out not getting the teacher we assigned them to, but a different teacher, we have to know that teacher's predicted effectiveness. So we have to predict for teachers who weren't in our sample where we don't have FFT or tripod, but we have value added. So this we can run on all kinds of samples and predict, whatever data you have, we'll run the regression and get the prediction. And that's what we did. Yeah?
Just do the second row there, add anything to the prediction?
I'll show you. Not when you have the first row. I'll show you. It adds a tiny bit, but not much. In fact, unfortunately, you'll see in a few in just a sec that even when you don't have this, sometimes these others aren't very strong in certain samples. So here's the regression. Here's what this regression looks like. So this one, think of this. This is just, I'm going to run a regression of last year's state value added as a dependent variable, and this is this year's state value added. Coefficient of 0.4, that's like a shrinkage of 0.4, which is kind of a standard shrinkage that you'd get from an empirical Bayes or these hierarchical model kind of predictions. Right? And that's totally standard, right? So here's your question when you have this and you put in the student survey and the classroom observation score, not doing you much, right? They don't add, and we have this other paper with the Mihaly et al. Paper where we make the point, if what you're about is trying to predict teacher impacts on state test scores, really all you need is value added. But it's not clear that's what the reason to collect these other measures is because that's not the only thing you want. The other reason you might want them is for some teachers you don't have value added, in certain untested subjects and grades, and this is kind of saying, suppose we just regress last year's value added and pretend, and ignore value added and just regress it on the student survey data. Well, that does have some predictive power. The student survey is significantly correlated with value added, right, with the teacher's value added in a different year. And same thing, barely, but there's a little bit of correlation with the classroom observation. This is all elementary grades, and this is math. In middle school grades, the classroom observation does better and is significant relative to this, and that's in the table in the paper. And then this is English language arts, and it's kind of a similar pattern, although here, really, the classroom observation is totally failing on us. This is one where Pam Grossman's had a way of measuring, instead of FF frameworks for teaching, of measuring English language arts performance. And that did seem to be a little more correlated with value added on English language arts. So that would have been one place where using that measure would have gotten a slightly different answer. Okay? But so these are kind of the regressions that predict, given the data we observe, what's our prediction of your effectiveness next year in a different year. Okay. So now we're set up, and I want to talk about this external, start talking about validity of the data that we have in the experiment. So on the external, let me summarize, and I'll show you a few tables. We've mentioned this already. It's within school. So we're only learning about, is this a valid comparison within school, not between. Turns out, and I'll show you this, the teacher value added in the participating teachers is similar to others. In some sense, they don't know their value added. It's not like they were saying, oh, I'm a low value added. I don't want to get in this experiment. Right? They'd never seen it. They didn't have the data at this point on it. This is the thing. The special ed and the English language learners are underrepresented, and that's for this mechanical reason that they couldn't be randomized. And this gets us, you'll see a little bit higher baseline test scores in our sample and a little less student classroom sorting, because a big part of the sorting is the special ed teacher always getting the low test score kids year after year. And we don't have that in our teachers. This is the value added comparison. So this is the mean in our randomized sample. This is mean teacher value added in the non-randomized sample. And then this is, in the non-randomized sample, but in the same school. So these are teachers who participated within and not in the school. And then in all the other schools in our MET, right? And so you can see kind of average value added similar, the standard deviation across teachers very similar, and same for ELA. So no selection going on there. This is on baseline, and let me walk you through this. So now we're going to compare, not value added, but baseline scores of the kids that the teachers get in our sample to other samples, and averaged at the classroom level. So first, just average baseline scores of the kids in our randomized sample is about 1/10 of a standard deviation higher, because we trimmed out those special ed and English language learners, right, compared to everybody else. This is the standard deviation in baseline scores across teachers. So it's the average baseline scores in their classroom. And this is the standard deviation across teachers. This is where 0.5, right? That's a standard deviation of, so 2 standard deviations means those teachers have average baseline scores of kids that are a full standard deviation apart in their classrooms. I'm just astounded by this. Now that's across schools. So really you want the within school standard deviation in baseline. So this is how much sorting is going on within school, and it's 0.4, right? And this is what I mean. It's a little less in ours. In the non-randomized sample, it's 0.5, and in the non-MET projects, it's 0.5. So there's a little less sorting, which we think is because it's ELL and stuff, but it's still a shocking amount of sorting. There's a lot of kids getting sorted to schools. This, by the way, this is 1 year, of value added. What we really care about is, does the same teacher get the low baseline kids year after year? So we had a way to estimate that I won't go into, but dealing with that, you still see like this is the persistent difference across teachers in the kind of kids they're getting sorted. There are teachers who year after year are getting kids who are 0.3 worse than average on baseline scores. So there's a lot of same teachers getting persistently better or higher or lower achieving kids. Okay. Yeah.
So you may be getting to this in the next section, but I'm thinking about the schools that when you said here's the random assignments, they said, oh no, we already assigned our teachers. Are they more like, and we don't observe the ones for whom the random assignment matched what they did?
Yeah.
Right. So are the ones that said, oh no, are they more likely to have have a bigger value here, or for the better teacher to be given to the better?
It's a good question. So so I'm going to show you some stuff on compliance. So this is the compliance question. So this is the sample who we randomized. But then once we randomize, who was it who said no, right? We don't actually have it quite that way. And now I've heard this question enough. We got to figure it out. Like, what can we find predictors of noncompliance? And was it in cases where, like, where the prior sorting had been really big? So they were willing. I see. So maybe they were willing to participate, but in fact they told us, "Hey, wait a minute. No, this teacher has to get the same kids she gets every year." That's a good question, and we don't know that. But I will show you some stuff. Like, I think that would suggest that the I think it would say that, well, I want to think about it. Like, I'm going to show you the way we think about noncompliance. Well, no, I'm not sure. Let's think about that as we get to the results. Because you're right, the issue is going to be, are the people who were willing to comply somehow unusual? Because we're going to end out estimating treatment effects. If you think of it as a local average treatment effect, we're going to get treatment effects for the compliers. And are they somehow different? And might they be unbiased, where the people who didn't comply were exactly the people where value added is a biased measure, right? That's the concern. And that's going to be a question that I don't think we have a good answer to right now. Okay? Okay. So this is, at least they didn't, when they agreed to participate, they hadn't thought that through. Maybe they waited until we told them what we were going to do and then said, wait. Okay, so this is about attrition. So think about, we had some attrition. It wasn't too bad of kids disappearing from the sample. Not related to the assigned teacher. So again, here's a summary, and then I'll show some tables. So it's not related to the teacher effectiveness that we assigned you. So it's not like we assign you a bad teacher and all those kids disappear from the school or something. And you'll see the student baseline characteristics are balanced. They're not related to the type of teacher, as they should be, both before and after attrition. They might be if we had systematic attrition, but they're not. The one that kept me up at night, think about our experiment. You randomly assign people these rosters, but then you can't stop kids from moving, right? Some gets undone. Now, normally you're fine. You say, oh, I've got my intention to treat group and but in this experiment, suppose that there's one kid who causes everybody's test scores to go bad through peer effects. He's the unruly child, right? And suppose that one kid undoes the randomization. We're dead, right? Meaning that means we randomized classrooms, but the key kid was undone and given to the teacher who he always gets. And once again, she looks bad because they gave her the one kid. And that is like a real threat to this if somehow the actual peers in the classroom resorted in a way that undid our experiment. So I'll show you that it turns out none of the results so both the assigned teacher effectiveness doesn't look like it's correlated with the actual peers who end up being in her classroom after noncompliance. And later, when we're doing regressions, we can control for the actual peers in the classroom, and this is another way of doing the same question. And none of the results seem sensitive to that. But boy, I'm still nervous about that, right? That on some unobservable way, the one unruly child. This is in part because my son was an unruly child who had these kind of peer effects on his friends in his classroom. Okay, so here's just to give you an idea of the attrition issue. So, almost 90% of kids had a state test score, so we didn't have a lot of attrition when we're looking at state test scores. And whether or not you had the state test score is completely, that attrition is unrelated to the teacher effectiveness that we assigned you. When we go to looking at MET outcomes, the MET test, that's only of kids who stayed in a MET teacher's classroom and who were there when we did the test and stuff. And so there we have a lot more attrition, right? Only 60% of the kids have the MET outcomes that we're going to look at. But again, unrelated, not significantly related to the teacher effectiveness we assigned, so it doesn't look like it's systematic attrition. This is the high school I mentioned, half the kids end out not having the outcomes, which makes us even more nervous. But again, not related. Okay? This is the peer measure. So again, we're regressing the actual measure of peers in your classroom. So my favorite, the average number of suspensions of the kids in your classroom. This is actually from the prior year, baseline year. And regressing that on your assigned teacher effectiveness to see if somehow the peers that you ended out with were related to the teacher who you got assigned. And we don't see anything. None of these are significant. And we look at absences and the usual demographics. So we're not seeing anything. Some of these are like the ELA scores, baseline ELA scores in math. That says if you're assigned to a teacher as a standard deviation higher effectiveness, the baseline scores of the actual peers were about a quarter higher. That's getting to be a magnitude I'm a little worried about, even though we're not powered for it to be significant. So that's saying the better teachers ended out, what got undone were peers who were a little better, moving back to the good teacher. Okay. So then the main problem. Let's talk about one of the big problems. So we've got this noncompliance. And here's what we're pretty sure. So we're pretty sure the noncompliance this was from our own discussions with people, was a logistical problem. It varies a lot by school and district. A lot of the districts, you sent them back the randomized rosters, and they said, oh, but we didn't agree to that. It was as if they had no idea they were in the experiment. We had all these guys who would say, so that's one example. The second example are all these guys who had already sent out the class list. We had a bunch of people tell us that. We already told parents. We didn't realize, I don't know what they thought, why they didn't wait. The third was after we randomized, a teacher goes on maternity leave, or they have to add another class and they redo the entire thing, right? And so those classes, some scheduling issue. So you tend to see most of the noncompliance. There's some noncompliance is a few kids switching. Not most of the kids stay with the teacher and a few switch. A lot of it is entire classroom, like just the whole thing blowing up and people going nowhere, right? Having nothing to do with how we assigned them. Okay, so that means if we just looked at the kids' performance based on assigned teacher effectiveness, that's like an intention to treat, so it won't be as big as we expect. So we want to think about how big we expect it to be. So we're going to do this IV, where we use your assigned teacher effectiveness to predict your actual teacher effectiveness. That's the first stage. And then see whether that prediction is related to the kids' actual test scores at the end of the randomization year. So this is, because it's IV, it's this, we got to give it this late interpretation, local average treatment effect. It's the effect in the people who complied with the experiment. And we should do something, you're right, like we have not done anything to look at the observable characteristics of the compliers compared to the non-compliers to see if it's obviously somehow systematically different. And so are we learning about a funny population here? Problem is, that's not perfect, because a lot of people comply because they would have not complied if we gave them the wrong assignment. This is why we can't just undo it in the data. But it'll at least give us an idea. You're more likely to not comply if your original teachers were really different on baseline scores. Or, I'll tell you what most of it is if you were in which districts? I'm going to see that in a minute. If you're in Memphis, right? If you're in Denver, a lot of this was very district-specific and school-specific. So what we're going to do is end out letting the compliance differ across schools and across districts. Here's a summary of some of the non-compliance, or one way of summarizing it. So Dallas is great, like good place to run an experiment. And even there, only about 2/3 of the kids who we randomized ended out with the teacher we assigned them to. This is, did you get a different teacher but within the randomization block? So we assigned you to A and other kids to B, and you ended up getting B. And that happened a little bit in Dallas, but not much. Most of what goes on is the kid moves totally different, to a completely different teacher in the school. Some of this is scheduling in the middle school. The kids change their schedule and aren't taking math 7th period, and so they're completely gone. Charlotte Mecklenburg, pretty good, but you can start to see like Memphis, Denver. It hardly stuck at all, right? Like the same. Kids were almost as likely to get the other teacher, the teacher we didn't assign you to, as the teacher we assigned you to. Like what a headache. So this is not great compliance. This is why we have to do this IV thing. This is like the first stage regression. And what we do, we've got to predict, for every kid, we have their actual teacher. And we know their actual teacher's effectiveness, which we estimated the way I talked about earlier. We can estimate that for every teacher. That's the left-hand side of the first stage. And on the right-hand side is the effectiveness of the teacher we assigned you, right? So this coefficient, so if we stack math and ELA together, this says on average, for every standard deviation increase in your assigned teacher effectiveness, your actual teacher only increased about 0.3. This is what killed our power. Like, thank goodness we had this study overpowered. Because we expected, think of, if this we expected this to be closer to 0.8 or 0.9. and it was 0.3 because of the noncompliance. If it's 0.8 or 0.9, let's say roughly 3 times as big, that means your standard errors are 3 times as small because you have 3 times as much variation in your right-hand side, kind of key right-hand side X. So our standard errors are about 3 times as big as what we had originally powered for. And so luckily they're still pretty tight, but it's a headache. The lesson is we should have gone for smaller sample and higher compliance. That's always the pay, right? Like this is equivalent to a sample size almost 10 times smaller than what we'd hoped for by getting compliance 3 times lower. Okay, and you can see it's similar in the math and ELA, very different across districts. This is Denver. Actually, there's no relationship at the district level between who we assigned, the effectiveness of the teacher we assigned and the teacher you got. Within districts, there's a huge amount at the school level. I think some schools were just unprepared. So what we're going to do is actually, in our main specifications, even let this first stage have interactions where at each school the compliance differs. And let me talk about that. Okay, so here's the meat now of the kind of the main result that's going to come out, or the main regression. So what we're interested in is we've got the student test scores in 2011. That's in the randomization year. We'll put some controls in for efficiency. We'll put in fixed effects for the randomization block because we're only randomizing within that. And then we've got the thing that we're interested in is whether your actual teacher's predicted effectiveness predicts the impact on your test score with a coefficient of 1. So if you actually have a teacher who's 0.1 higher on teacher effectiveness, does that lead to a 0.1 higher test score? That's the forecast unbiased. Actual teachers endogenous, people sort. So we want to instrument for actual using your assigned, which was random, right? And that's the idea. So use random, your assigned teacher effectiveness as an instrument for actual. How are we going to do this? So we're going to do, here it is. We're going to interact your assigned teacher effectiveness with a bunch of school dummies. So that's a huge number of instruments in the first stage. That turns out is equivalent to, there's this nice paper by by Imbens and Chamberlain that says, suppose you have tons of little experiments. Each school is its own experiment. And you estimate IV in each school. What's the optimal way to combine all those IV estimates to get one combined efficient estimate? Turns out if you estimate liminal, which is a type of instrumental variables, using all these interactions, that's equivalent to the optimal way of combining all the experimental data. So it's like an optimal meta-analysis of the individual experiments that were run in each school. So that's what we do. We run this, we run liminal. Since I like thinking about weak instruments, if you've got a weak first stage, you can get in trouble. With liminal, if you've got a first stage that's basically where the first stage S over 2, even with this many instruments, you're in good shape. So this also has good properties from that sense. Okay, so that's the basic idea, and think of it as we've got each of these experiments, each with their own compliance. We get all their individual IV, and then we combine them together with liminal to get the overall estimate. The other thing that actually, and it's not critical to the results I'm showing you, but it does matter, and we did it like Chetty did. And I always do this to highlight for people, if you're really doing this in practice with the district, we dropped the top 1% of the teachers with the 1% of teachers who had the highest value added are fishy. And there are lots of things that suggest they're fishy, that something's up with them. And Chetty et al. Found this. And sure enough, in the randomization, they look a little bit off the line, like they are not predicting. They aren't having the impact you'd expect. The other thing, for us, we had the alternative test that we'd given. And there was a teacher in here who all their kids basically got a perfect score on the state test, and they were very average on our alternative test when we gave it. So there was a lot to suggest that somebody should be auditing those guys, and we dropped them, right? Just got rid of them. if you put them in, the overall result doesn't matter. It has a little bit of an effect on the ELA result. It flattens it out even more, because that was where it seemed to be the biggest outlier. Okay, so that's the run. Nobody's giving me a hard time. Every once in a while, somebody mentions there's this paper on LIML by a grad student who came out of Harvard a year or two ago that claims that it's very hard to know what LIML estimates. That I think the way he puts it is LIML estimates nothing in particular, which is a somewhat strong statement. In this, it turns out that's a question. If you think there are heterogeneous coefficients, and you're trying to estimate like an average coefficient in these late kind of interpretations, then LIML is difficult to interpret because it's a statistically weighted average of a bunch of different estimates. And what is that? Like, how do I interpret that in terms of some average across people in the population? In our thing, our null hypothesis is that this coefficient is 1 and for everybody. And under that, LIML is the optimal estimator. So we avoid them. So I just raised the problem and tried to dismiss it. But it's something to know. Like, whenever you're in a crowd who knows that, they always say, "Oh, but doesn't LIML have these problems?" And I'm like, no. Okay, so let's get to the result. So here we stacked up math and ELA, right? Because they all expected to have the same coefficient of 1. We've got controls for the students' prior achievement demographics, which help a lot with power, especially with our low compliance. No controls for peers, right? This is 27,000, so it's all the students who we randomized and had a state test, which is the left-hand side variable on. And this is the coefficient on the teacher's expected effectiveness, right? And that's a coefficient pretty close to 1. Plus or minus 0.25, right? Like in terms of confidence intervals. This is where we powered this to be, have a confidence interval that was plus or minus 0.05, 0.06, something like that. So we're not as powered because of the lack of compliance. You can split it, math and ELA, and this is basically exactly coming from the pictures I showed you early, right? Math has a coefficient basically 1. ELA a little below, but you can't reject 1. And the key is all of these, you can't reject 1. They're pretty close to 1. You can clearly reject 0. So these things are predicting the teachers who you think are more effective are significantly higher outcomes when you randomize, right, is the way to interpret it. Right? You can do the no controls at all. Coefficients are quite a bit noisier, but all the same conclusion, can't reject 1, can reject 0, but a lot noisier. This last one says, I told you I was worried about peers. What if we put in controls for the actual peers in the classroom? Because we're worried those might have been undone in a systematic way. And, none of these results are at all sensitive to that. So the actual peers are not driving anything going on here. So that's the kind of, bottom line, ones, a lot of ones. So that's the forecast unbiased. Let me just show you, this was all using exactly the assigned teacher interacted with the school, teacher effectiveness interacted with the school as instruments. Let me show you kind of what happens if you do it other ways. So what if we put no interactions? Just run, the first stage is just your actual teacher effectiveness regressed on your assigned teacher effectiveness with no interactions. Coefficient's still close to 1, significantly greater than 0, but it's a power issue, right? Like, here's the one we ran, interactions at the school level. Here's if you have no interactions. If you do interactions at the district level, which was like that table I showed you at the start, and let compliance vary by district, you're already pretty close to where we were. Go to the school, it's a little tighter. You can go all the way down to, you can think of each randomization block as a separate experiment, but there basically isn't much action within school at the randomization block. It's really at the school level where the compliance differences occurred. Okay? And so, all looking like 1. the last 3 columns ask a different question. So instead of changing how we do the instrumenting, it says, what if we estimate teacher effectiveness different ways? So the first, Susanna, you had asked, like, does it matter if we only used value added to predict the teacher's effectiveness rather than and ignored frameworks for teaching and student surveys? And the answer is, you get an answer that's very similar and similar precision, a little less precise. So these other things, when you include them in, generate a bit more variation in the right-hand side variable, in the predicted effectiveness, and that gets you a little more precision, but it doesn't really change the answer much, right? They don't do much. More interesting, suppose you only used, suppose you didn't use the value added to predict teacher effectiveness. You only used the frameworks for teaching data. And does that then also, so then that gives you a prediction of each teacher's impact on test scores. And sure enough, that's still significant and not different from 1. So those are also look like they're valid predictions of which teacher, if you had nothing else, they're still useful. They predict which teachers will have positive impacts, and they predict the magnitude about right on kids' test scores. But they predict like Sean said, right? They're predicting much less spread than the other measure. When getting value added in there predicts a lot more spread. And same thing, the student survey similarly predicts significantly, not different from 1. So any measure, all these measures seem like they're able to get you unbiased, forecast unbiased predictions of teacher effectiveness and significantly distinguish between teachers, right, is the bottom line on this. Okay. Yeah.
So how biased, this is more like the confidence interval, how biased would it have to be?
Yeah. So like on these, it would have to be really bad, right? Like I wouldn't have power given these confidence intervals, even if it was 0.5 or something, I wouldn't have power, right? For this, you're right, like this, or wait, where's my favorite? For our favorite, this includes, it could be that teachers are, 25% better or worse. We have bias of 20 to 25% on these. They're still, it's not enough to flip it. Like you'd still say the teachers who are better on value added do have bigger impacts. Maybe not quite as big, or maybe a bit bigger than what we've estimated. But this still, like that's why we wish this was tighter. The compliance hurt there. But it's better. The Raj Chetty paper, which uses the quasi-experimental and a gazillion years of data, has standard errors of about 0.03. Jerks. They got tighter estimates. That was what we went in this planning to have at the end, had we had the compliance that we expected. So, but still, it's there. That's why, so you're right. There's a possibility, but in some sense, one way to say it is, if I was going to select a teacher for something, say as a parent or whatever, based on their value added might be 20% bigger or smaller than what I see. So instead of 0.1, it might be 0.12 or 0.08, but that's kind of the range of the likely impact. Now that's on average, right? I have to be a little careful. That I said that like it was about an individual teacher. Individual teachers might be a lot more or less. But at least there's no evidence here that says observational value added data is misleading us. It looks like it's pointing us in the right direction. Okay. After you see enough regressions with coefficients of 1, you start saying, you probably get coefficient of 1 no matter what you do. So at least I can do some things where we won't get a coefficient of 1. So let me show you some of those. So this was our original. This is, okay, now let's be really dumb. Right? So I'm going to have to pick something pretty bad to make it go really bad. Let's not control for anything. I'm going to use mean test scores at the end of the year, not even control for baseline test scores, mean test scores of your kids. So that any student sorting shows up in that, right? That's biased, right? It's still a significant predictor. People whose average test scores at the end of the year, their kids actually do better when you randomly assign them. And that's because better teachers are getting assigned better kids at baseline, right? and because they actually have a positive effect, just not as big as you thought based on the baseline. So, but it's not 1, right? Which is the, and then if we didn't do shrinkage, right? This is obvious, right? If we shrunk, which meant we took the estimate and multiply it by about 0.4. If you didn't do that, you'd get a coefficient below 1. You get a so if you just used raw data and thought that was true and didn't do the shrinkage, you'd overstate differences across teachers by, over half, right? Almost twice as big as they actually are. Okay. Let me close with one. Oh no, let me show this, and then I'll talk about the last thing I'll close with. So this was all on test score stuff. So this is the table looking at, these are the exact same regressions, different samples, because it depends. Now the kids have to have this outcome, and that's only the kids who are in a MET participating classroom. But now we look at other outcomes. So this is the supplemental test, BAM and math, and this is stacked math and ELA, but it's similar in the two. So this is, if you got a teacher who was better on state test value added, you also did better on the supplemental test significantly, but not the full standard deviation better, so not as much, but better. Some related to grit. Maybe that's because our measure of grit is lousy. Maybe that's because grit is a different dimension. Teachers who are good on value added don't have impacts on grit. Or maybe that's because teachers don't have impacts on grit.
I think, psychologists here, grit is not supposed to be something you move. I thought.
I'm open.
Yeah.
Well, that's consistent with this, although I thought they were trying to teach grit. I thought that's what Angela Duckworth's been doing now.
I thought she said that you can't. Oh, people who do this. You're not supposed to.
I don't think that there's a clear. I think it's ambiguous. I think they kind of said things that sound like both, sound like this is really sort of like a trait of people that's fixed, and yet they're doing interventions to try to improve it.
You know what? I would love, so we didn't do it here, and we only had grit as an outcome in the randomization year. We didn't collect it in the observational year. But even using that data, I'd love to see if there are teacher effects on grit. Like just do standard value-added models. I can't control for baseline grit, but I can control for baseline test scores and stuff. And are there significant mean differences in teachers on their kids' grit at the end of the year? I'd be, it's like the old value-added literature. It's a start, and maybe eventually we'll convince ourselves it's real, but I'd be curious about it. Yeah?
So, Doug, you mentioned earlier that classroom observations didn't predict future performance, conditional and value-added.
Yeah.
Do the classroom observations predict these? I'm asking because they're so widely.
Oh, that's a good question. Yeah. I don't know. I have a feeling we did. I don't know the answer. We might have done it, and I've forgotten the answer. But that's a good question. In other words, one reason we might want to get classroom observations and these other measures is they predict non-test score outcomes better, right? And they'll tell us, oh, this is a teacher who will have big impacts on grit or whatever. And I'm pretty sure we never looked at grit. I do have a feeling we might have looked at the happiness, but I'm pretty sure we never looked at it in the randomization, which is what we really want to know. I think we did some of this observationally in earlier reports, but that's a great question, right? Because that's one of the reasons you'd want to collect that data. They proxy for impacts on other non-test score outcomes that teachers have. It's a great question. I don't even remember what implicit theory of intelligence was, but it was something that somebody was interested in, and we measured it, and it wasn't significant.
We know what that is.
You guys know. I know. I'm just showing my general ignorance of things. But the student effort, which we thought, you can tell a lot of stories where effort might be affected, where it might offset and stuff. So this is, but nothing. But this, by the way, is measured also in student-level standard deviations of a happiness scale. This student enjoys class. So these teachers are also, their kids are a standard deviation higher than other kids on the happiness scale, if for every standard deviation higher on kind of test scores the teacher's pushing them, which I find really surprising. I think I was a bit surprised by that. Okay, so that's the other outcomes. let me close with, and this is probably the most surprising thing, and it's a little buried in the paper, that I think came out of this, was when we started thinking about, have we over-controlled for peer effects? So here's the issue, right? We ran this regression where we controlled for like average peers in the classroom, average peer characteristics. That just removes any correlation between the teacher effect and peers. But that might be real teacher. It might be that good teachers get assigned to different kinds of kids. The principal does that to try to keep the good teacher happy or whatever. So you might ask, did that piece we removed by sweeping out anything correlated with peers, was that peers or was that the teacher? Would it stick with the teacher when we randomize them? In which case you shouldn't remove it, at least within school. So this is all about within school comparisons. So we wanted to ask that question, and we did it a pretty simple way. We have our measure, our original measure of teacher effectiveness that had removed the peer effect. Go back and redo everything, but get these controls out of there. So don't control for peers. Leave it in there. And get a measure, this thing I call no peer controls. The difference is the component we removed when we controlled for peer effects. So the difference between what I think if I don't control for peers and what I think if I control for peers. We can put both of these into our regression, instrument both of them the way we did, and see whether, so we've already learned that this one has a coefficient of 1. Is the part that we removed by peers, does it have a coefficient of 1 or a coefficient of 0? Right? It should, if it's peer effects, it should be 0. It doesn't go with the teacher when we randomize. So, and by the way, you can do that for other components. Stop controlling for other things. Drop out other controls and keep checking those components. So here's our original regression. Here's when you include, so that same original variable that's removed the peers. And here's the component we removed with peers. Coefficient of 1, significantly different from 0. In other words, whatever it was about test score gains that seemed to be correlated with having good baseline peers was a real teacher effect. It went with the teacher when we randomized them within school to classrooms. Totally, I totally did not think that was the case. This would suggest that within school comparisons should not control for peers. They're basically, the peers are a signal that this was a better teacher and will actually be a better teacher when they go to even if you gave them very different kids. It also says something probably about what principals are doing when they're sorting, right? They're actually thinking about trying to give good teachers different kinds of kids. This is not about between school, right? We're trying now to use the Raj-Chetty approach in Los Angeles data to think about this between schools. Does the peer effect move between schools, not just within school? You can do this, the component that you remove by student demographics, it's not enough variation. You don't remove much with student demographics. So it's 0, but a big standard error. This is the obvious one. The component that we remove by just controlling for student baseline scores, well, that's 0. Those student baseline scores, that's not something you want, right? You want to get that out of there. So, this approach, I think, is pretty interesting. I think this approach of breaking it into components and seeing if different components predict is useful. Like you can use the exact same thing in the Raj-Chetty kind of style natural experiment studies. Okay, so what would I come away from this and all the other work that's been done recently kind of thinking, it is very hard for you to, there's just a lot of evidence that the value added is actually capturing causal effects, at least within schools, of teachers on state test scores, right? Which was what it was supposed to measure, right? And I just think they aren't perfect, so there's a lot of parts of teacher effects on test scores that they haven't predicted, but what they have predicted is accurate or unbiased, forecast unbiased. To me, and I've been feeling this way now for a while, I just feel like we've totally gotten focused on the wrong issues in this whole literature. We worry about all the methods and controls and should we do this and should we do that and methodology. And I think really the issue is, okay, but do we care about teacher impacts on state tests? It's basically, it should be an argument about what's the dependent variable, not have we done the controls to get at causal effects. And there are real issues, impacts on state test score at the end of this year, but what about by next year? The fade out kind of issues. Do we care only about test scores, state test scores? Should we really be thinking about these other non-test score outcomes, right? To me, that's the issue, is trying to get better measures and data on other outcomes. Or should we be using these other proxies because we think they're correlated with other outcomes that we've never measured? I'm a little nervous about that. I'd rather try to measure them. But that, to me, is the debate we should be having.
So is there any lessons from the medical? So you have this other Pat that does the same sort of stuff. What are there lessons from the way that debate has gone, or what's been learned there, that we ought to be thinking about in the education one?
Yeah, I think there's there's a couple of lessons. One is, everything that you hear from teachers and people when they don't like these measures, you hear from doctors. But I think the medical world has totally bought into it now, into the measurement. And the reason is probably that the way it's been done in medicine, there were some kind of top-down performance measures and trying to penalize doctors, but not much. Mainly what's happened is groups of doctors have gotten together, like all the bariatric surgeons. They gather data, they create measures, they look at it, and the person looks at their data and says, oh, something's wrong, like my patients are different, the data's wrong. And then someone goes to them. There's a great story of this guy who runs a big collaborative in Colorado, and he said, oh, you're right. I'll come out to your hospital, and we're going to sit down with all your data and go through patient by patient and figure out what's wrong. And, of course, there's nothing wrong, and their patients are the same as everybody else's. So they built trust, and now people use these, and they understand they're limited, but they've helped design, part of what they didn't like were the measures were one size fits all. And so they're like, no, I need particular measures that are relevant to the clinical thing in bariatric surgery, right? And I need to have adjusters that, that I find plausible and buy into. And then they've used it for quality improvement more than high stakes accountability, although it's moving in the high stakes accountability way, and I think people are comfortable with it now. So, but all the same thing, actually, I'll tell one story. The first time they put out mortality measures, just, an example of how you ruin trust. Medicare created mortality measures for heart attacks for every hospital in the country and posted them back in 90-something. And the worst hospital in the country was a hospice, right? Of course they had high mortality, and they just had not been very careful with the data, and immediately, this is silly, and it basically set them back for maybe 10 years, right, in terms of putting that data. They've just, in the last 5 years, started Medicare puts that data up now publicly. But, so I think, one of the lessons is using it in a sensible way, and, they aren't using, people pay a lot of attention to it, and the medical director at hospitals are going to talk to people and saying, look, what is going on with your rates? You've got really high infection rates, you've got really high whatever. And people are taking it seriously that way, but they're not using it to name and shame or in a arbitrary bureaucratic way, right? It's a very well managed, or where it's working most successfully, it's well managed. I work with some of these. And that's where and I have this business that does this too, so I'm maybe rose-colored glasses because of the business side on this. But that, to me, that's really the worry, I'm sure, as soon as it starts being formulaic in schools and seems like it's coming top down, I'm a bit worried that it won't get the buy-in that you get. Yeah.
So I'm curious, if the policymaker would come to you asking you, your study is great, you have all this predictive unbiasedness going on, yet it's still just an average effect.
Yeah.
And so there's a lot of noise for a particular teacher. What would be your prescription on how you actually would use this in practice when districts are really looking to evaluate individuals?
Yeah. Here's the thing. The way I always think of this is, you can get not only the prediction, but the confidence interval in a Bayesian sense, the prediction out of these is my best guess about your performance based on the data I've seen so far. But there's a range. You might be as good as this or as bad as this. But being able to tell somebody, well, there's a 5% chance you're better than, or 10% chance you're better than average, but there's a 50% chance you're worse than a rookie. And so, okay, we might be wrong, but I'm not wrong on every teacher in the school, right? It's supposed to be only 5% are better than average, not everyone. And so I think using that in a way where you give people, where there's realistic, where you understand what it means to be low, predicted low performing. There may be some extenuating circumstances, and you might be the 1 in 20, but you got to make the case, right? The evidence is that most likely you're not, and unless there's some really good private information that your data is misleading, you shouldn't go there. So like I always, when people get this, like when doctors get this, it's like, look, this doesn't look good. Maybe you wait another year and you get another, and you don't ignore this year's just if next year's better, but I start accumulating more data and averaging it. But it's not. I think like our local schools have been doing things like this, and they're willing to say, there's enough here that I think you're actually a good teacher, and this was bad luck, but let's keep watching it, because it's not it's not always bad luck, and not all of our teachers are bad luck. Right? So it's a tough, right? But this is what every manager has when you've got no data's perfect. You got a lot of stuff. I think there's not. I'm not sure principals or the people making these decisions have the skills, have been to do this management. It would be nice, if we could develop that more.
I hate to cut this off, but we're over.
Great. Oh, sorry.
And we can talk outside because there's a conversation.
Okay.